Well, howdy. On this example, we're going to actually solve a time problem. A time problem is where you're solving for the number of periods or the number of years for an investment to grow to a certain amount. So here, let's take a look at this example. In this example, we have $7,000 and we want to buy a $10,000 automobile. So what we want to know is how long it will take the $7,000 to grow to $10,000 if it's invested at 9% annual rate compounded quarterly. Now on these problems you always round up to the next higher quarter or period if it's not exact. So actually, since we know this is a lump sum, this $7,000 is just a one-time investment. So it's a lump sum, and we know we have compounding here because it says compounding right there. So we know that we should be able to use this formula here to answer the question. So let's look at what we're given. We're given the principal is $7,000. We know the amount we want it to grow to is $10,000. We know our annual rate of return is 0.09. We know we're compounding quarterly, so M is 4. And then we know I would be 0.09 over 4, which is actually a terminating decimal, 0.0225. And we want to know the total number of quarters. So we want to solve for N. We want to know how many quarters it will take that 7,000 to grow to 10,000. So basically, we're just going to plug everything into this formula. So we're going to plug the 10,000 in for A. We're going to plug the 7,000 in for P. We're going to plug the 0.0225 in for I. And N is going to be left as N. Well, then I'm going to divide both sides by 7,000. So if I divide this side by 7,000, it'll just cancel the 7,000. And then if you divide 10,000 by 7,000, you'll get 10,000 over 7,000. But I went ahead and reduced that to 10 over 7. So I get 10 over 7 equals 1 plus 0.0225 raised to the N. Now since I can add these two numbers together, I'll just go ahead and write that as 1.0225 to the N. Now, when you're trying to solve for an unknown exponent, one little trick we have up our sleeve is to use log properties. So what I can do here is I can take the log of both sides of this. Now I don't care whether you use the natural log or the common log, but I'm going to use the natural log. So I'm going to take the natural log of both sides. So if I take the natural log of the left, I'll just get natural log of 10/7, and the natural log of the right gives me natural log of 1.0225 to the N. Now there's a property that says that anytime I take the log of something to the nth power, I can write that as N times the log. So there's a log property, you might have to go look it up, but there's a log property that says the natural log of 1.0225 to the N can be written as N times the natural log of 1.0225. Well, once I get to that point, I have a natural log of 10/7 on the left, and that's just a number. And over here I have N times another natural log, which is also a number. So if I just divide both sides by this log, so just divide both sides by this natural log, and then that'll give me N on the right equals the natural log of 10/7 divided by the natural log of 1.0225. Now, I got N equals 16.03, but that tells me that 16 is not enough quarters because I need a little bit more than 16 quarters. So it's actually going to take me 17 quarters for the money to grow to $10,000. So that's how you solve that problem where you have to solve for N. Now, one of the things that we need to talk about in this section is called annual percentage yield, which is APY. And what annual percentage yield, it allows you to compare two different investments that may have different compounding schedules and different interest rates. So for instance, if you had the option of investing your money in Bank A that pays an annual rate of 3.95% but compounded monthly, or Bank B that pays an annual rate of 3.98% but compounds quarterly, which would be better? Well, if you just look at these, try to compare them apples to apples, obviously the 3.98 is better than the 3.95 that you have up here. But in Bank A, you've got monthly compounding right here, whereas in Bank B, you have quarterly compounding. So the question is, which is better? Is it better to have the lower interest rate but better compounding, or is it better to have the higher interest rate with worse compounding or lower compounding? So the question is, which would you choose? Okay, well, I'll let you read this, but I'm just going to go ahead and give you a formula. The formula can be developed, the APY formula can be developed by actually setting the simple interest rate formula and the compound interest formulas equal to one another, because what you're really looking for here is the APY is really just the simple interest rate that will give you the same return as your compounded rate. So when we find the APY, we'll actually get the simple interest rate that's equivalent to our compound interest rate. And so let me show you what I mean here. But let me give you the formula first. The formula for APY, annual percentage yield. This is also, by the way, called effective rate. But it would be 1 plus R over M raised to the M, not N, but raised to the M minus 1. So let's apply this to Bank A. Let's calculate the APY for Bank A. Now remember, Bank A had a rate of 3.95% and it was compounded monthly. So if we calculate the APY, we would have 1 plus 0.0395 divided by 12 raised to the 12 minus 1. And that gives me 0.0402. Well, that would be 4.02%. Well, what that means is it means it would take a simple interest rate of 4.02% to match this compound rate of 3.95% where money is compounded monthly. So it would take a 4.02 simple interest rate to match this. Now let's look at Bank B. Bank B, we had a rate of 3.98% compounded quarterly. So if we calculate the APY for Bank B, then that would just be 1 plus 0.0398 divided by 4 raised to the 4 minus 1. So we would get 0.0404, which is 4.04%. Okay, so now you can see that it would take a simple interest rate of 4.04% to match this annual rate of 3.98% with quarterly compounding. Well, since Bank B, since its APY is actually better than the APY for Bank A, then Bank B would be the better choice to invest your money. And that's all it is. And so if you want to find which is the better investment on two investments that are so close it's hard to tell. So again, here, 9% compounding monthly, you got the better compounding periods here because you're compounding monthly. But here you got the better interest rate, 9.1%. So all you do is apply this formula to each one. So if you apply the formula to the 9% compounded monthly, then you would get 1 plus 0.09 over 12 raised to the 12 minus 1, which is 9.38%. And then if you apply it to 9.1% compounded quarterly, the APY would be 1 plus 0.091 over 4 raised to the 4 minus 1, which is 9.42%. So it looks like, again, the second example, the second choice would be better. Okay? Now, another question you might be asked is to find the annual percentage rate that corresponds to a given APY. So let's say you have an APY of 3.295% and you want to find the APR that corresponds to that. Well, if you're going to find the APR that corresponds to that, you got to know your APR, what the compounding schedule is for your APR. So here I've given you that we're going to assume quarterly compounding. Okay, so basically what you do to solve this is you get the APY formula and you plug in the APY you were given in decimal, 0.03295. And then you have, you plug in M. Let's see, we had quarterly compounding, right? So we plug M in here and here. So we plug 4 in there. And then we just solve this equation for R. Now this is kind of a weird equation, but if you take it step by step, it's not too hard to solve. It's just got some weird things to it that you have to do. So here, if we add 1 to both sides, so add 1 to both sides, and that'll cancel that. And then when you add 1 to this, you'll get 1.03295. Now, what you're going to have to do next to eliminate this power right here, you're going to have to take the 4th root of both sides. And so if you take the 4th root of 1.03295, you're going to get this, the 4th root. And if you take the 4th root of this expression on the right, notice it just gets rid of the root. So now, to finish solving this for r, subtract 1 from both sides. And if I subtract 1 from both sides, I'll get this root minus 1 equals r over 4. And then to solve for r, just multiply both sides by 4. So r equals 4 times that root minus 1, which is 0.03255, or 3.26%. So in other words, APY of 3.26% compounded quarterly is equivalent to, a rate of 3.26% compounded quarterly is equivalent to an APY of 3.295%. Now I'll let you pause the video if you want to, and then you can do the same thing if you assume monthly compounding. So here you can do exactly the same steps I did, but remember, with monthly compounding you would plug 12 in for M. Okay, but you would still go through basically the same steps. And you see here that my answer is 3.25%. Okay, I've got one more video on this section that I'm going to use to show you 3 more examples. So you can look at those in the next video.